Welcome to this explainer. Right, so today we're digging into a seriously fascinating question right at the bleeding edge of aerospace engineering and computer science. We're looking at a case study from August 2026, and we're investigating whether a synthetic aircraft simulator built by DB Bavoon LLC actually managed to predict the real-world outcomes of a massive $6.5 million drone competition. And this isn't just about drones. It's really about whether the virtual sandboxes we use to design our future can actually reflect the messy, chaotic reality we live in.
So here's the hook. We're asking if a completely independent, physics-based simulator can actually predict which engineering teams are going to win a high-stakes competition. And here is the absolute kicker. This simulator was built entirely from scratch, zero calibration. It was not fit to any real-world competition results whatsoever. It literally didn't know who was going to win. So if we take real custom-built drones and feed them into this completely blind simulation, does the code actually know a champion when it sees one?
Okay, let's dive into this. The battleground for this test was the DARPA Lift challenge. The premise? Brutal but simple. You had to design a vertical takeoff aircraft capable of carrying a payload that is at least 4 times its own empty weight. 4-to-1. That is a staggering payload-to-aircraft mass ratio. You had to take off, fly a loaded outbound leg, drop that massive payload, and fly all the way back to land, and do the whole shebang within really tight time and altitude limits. Out of roughly 100 teams that entered this absolute gauntlet, only 5 actually completed a scored course. Now, nobody hit that magic 4-to-1 ratio, but Aviar drone came incredibly close. They took first place with a 3.84-to-1 ratio, bagging a $1.25 million prize. The top 5 are Aviar drone, MTech, Extreme Aerial, H-squared, and MacGyver down at 2.51-to-1. But check out that 6th team at the bottom, Defentex. They didn't finish. Actually, they crashed, attempting a completely massive 6.11-to-1 payload ratio. We're including them in this analysis, though, because they're the only crash team that left behind enough public data to actually analyze. So how exactly do you test a simulator against these real results when all the teams keep their blueprints highly classified? Well, the researcher had to forensically reconstruct these 6 real aircraft. They pulled from public photographs, competition videos, telemetry overlays, even social media posts to use as inputs. It's kind of like a giant puzzle. They took these estimated real-world specs and dropped them straight into the simulator's random failure mission model, just to see if the virtual physics engine would bless them or doom them. Part 1. The inverse ranking trap. Now, what happens next is an absolute masterclass in testing your scientific assumptions. Before finding the truth, the researcher fell headfirst into a massive methodological trap. Just look at the sheer scale of the failure in this initial data. The first time they ran these reconstructions, they used naive, hand-tuned point estimates for the unknown variables, basically making their best single guess for things like battery mass based on photos. And the simulator? It spat out a ranking that was a perfectly inverse, completely backward correlation. No way, right? Avia Drone, the real-world first-place winner, literally scored the absolute lowest in the simulation. Meanwhile, MacGyver, the real-world 5th-place finisher, was crowned the virtual champion. If the researcher had just thrown their hands up and stopped here, they would have concluded the simulator was actively opposed to reality. But they didn't stop. They knew something was off, so they kicked off a rigorous debugging process. Instead of just single guesses, they used a Monte Carlo analysis. We're talking testing hundreds of thousands of random, plausible guesses for the unknown specs to figure out what on earth was causing this wild variance. And through controlled testing, they found the bug. It wasn't the physics engine at all. It was human error in the reconstruction inputs. The researcher had accidentally given the simulated drones inconsistent battery energy capacities. So some drones were virtually starved of power simply because of how their battery weight was estimated. Once that sampling artifact was fixed and the battery capacities were properly aligned with the actual mission requirements, all that massive, chaotic variance just collapsed.
Part 2. The percentile true.
So, after all that, we were left with a tight, accurate band of data, which brings us to the actual honest findings of the study. And this brilliantly illustrates that while the simulator obviously can't perfectly predict the fine-grained differences between 1st, 2nd, and 5th place, it absolutely can recognize a winner. When benchmarked against 150 completely random designs generated by the simulator, all 5 real-world winning drones landed solidly in the 70th to 77th percentile. They didn't land in the middle of the pack, and they sure didn't land at the bottom where designs crash right out of the gate. The simulator correctly identified all of them as solidly above average, highly viable engineering solutions. And this gets even more compelling when we zoom in on two specific teams, MTech and MacGyver. See, a few of the real-world drones were single-main rotor helicopters, which is a design the simulator's code couldn't perfectly replicate without making some minor categorical substitutions. But MTech flew a hexarotor, and MacGyver flew a quadcopter. Those architectures, they could be represented perfectly, with absolutely zero approximation in the code. And guess where they landed? Both of them, completely independently of each other, landed at the exact same 71st percentile in the simulation. How cool is that?
Now, you might be wondering, if the real-world winners are hanging out in the 70th percentile, what on earth is sitting in the 99th percentile? Are there just these super drones out there that we haven't built yet? Well, the researcher did a mass budget reality check, and it turns out the absolute top-tier simulated designs aren't necessarily buildable in the real world yet. The generator often unrealistically allocates over half of a drone's total weight just to batteries and landing gear, which leaves virtually zero mass budget for motors, frames, or wiring. So placing in that 70th to 77th percentile, that might actually be the absolute ceiling for what is physically possible with today's materials.
Part 3. Discovering design levers. So, now that the simulator has been totally validated as a consistent, reliable screening tool for general viability, how do we actually use it? Well, the researchers shifted focus to see if this virtual sandbox could uncover actionable design improvements, stuff engineers called design levers. They used the simulator to test potential upgrades on the real winning drones. And the most fascinating result came from combining a higher battery energy margin with an 8% lighter airframe. You'd think making a drone lighter to boost its payload ratio would just make it more fragile, right? And for 4 of the teams, it did. Their simulated reliability dropped. But for MTech, this exact combination was a total magic bullet. It improved their ratio to nearly 4-to-1, while simultaneously improving their reliability. The simulator didn't just spit out generic advice. It found a highly specific, design-dependent upgrade.
The researcher then took things a step further. By looking at the broader population data within the simulator, they spotted 2 trends among the highly successful virtual drones. They had specific touchdown and climb rates, and they had faster cruise speeds. Now, to figure out if these were real, actionable levers or just complete coincidences, the researcher pitted them against each other in a controlled verification test. Let's see how this builds, because by applying these tweaks directly to MacGyver and MTech in the simulation, a very clear winner emerged. Tuning the landing gear robustness relative to the descent rate was a massive success. It netted a huge 4.3 percentage point reliability gain for MacGyver. That is literally the single largest gain found in the entire study. On the flip side, increasing cruise speed completely failed to replicate the benefits it showed in the broader population data. It was just a phantom correlation. So the simulator proved its worth by effectively separating the real engineering levers from the fake ones.
Part 4. Reality versus simulation. All right, as we wrap up this explainer, we really mean to bring these incredible findings back down to earth and answer our core question. What can synthetic environments actually achieve for us in real-world engineering? So the crucial point is exactly what the researcher concluded in their paper. We should absolutely embrace these simulations. They are fantastic, highly defensible screening tools to figure out if a design is fundamentally viable. And they are brilliant at discovering testable design levers, like that landing gear tuning we just looked at. But they are not crystal balls. They simply cannot predict whether you're going to finish in first or second place. Which leaves us with this final thrilling thought. The simulator correctly identified the champions, placing them all safely in the 70th percentile and up. But the real world? It's messy. You've got unexpected gusts of wind, tiny manufacturing defects, pilot nerves. It's a lot. If our absolute best physics simulations can only reliably get us to the 70th percentile of understanding, what unmeasured, beautiful, real-world chaos are we still failing to model? It's an exciting frontier for sure, and it proves that the engineers on the ground are just as absolutely crucial as the code in the machine. Thanks for joining me on this explainer, and keep questioning the data.